In this video, we are going to learn about autoencoders. So these autoencoders were first introduced by the godfather of AI, Geoffrey Hinton, in 1980s, and the word auto in the autoencoder means self in Latin. So that's why they are known as self-supervised machine learning technique or unsupervised machine learning technique. This means they don't need labels. All you need is just input data. So autoencoder consists of two main blocks, the encoder block and the decoder block. So the encoder block reduces the high dimensional input data, which in our case is going to be an image, into a low dimensional latent variable. So we are going to go from like 28 by 28 by 1 in case of MNIST to just two variables, so that two variables will have all the information about a particular image. And then what the decoder does, it converts that low dimensional latent variables back into high dimensional input data. And sorry for the typo mistake, it's not that, it's data. So the input of this model will be 28 by 28 by 1, and the output will also be 28 by 28 by 1. Now let's see the general architecture of this model. So this is a general architecture. We will have the input, then we have the decoder, and then the latent space. So in our case, the latent space is going to be 2 because we are going to use the MNIST fashion data set, but you can put here any value. It could be like 32 or 64. So for example, if you are training this model for celebrity data set, then the latent space might be 64 or 128, so that it could easily store all the information of the images. Then the decoder is going to use that latent information in order to convert it back into the input image. So like we are compressing the image first and then we are decompressing it. Now let's talk about some of the code. Obviously we are going to learn the code in detail in the next video, but this is like a general overview of how the code is going to look like in case of encoder and in case of decoder. So first of all, in case of MNIST, I'm going to use only two convolutional layers. If you have a large data set, a more complex images, you can increase the number of convolutional layers and the filter and kernel size accordingly. So the first convolutional layer will have 32 filters with 3 kernel size, and the stride will be 1. This means the spatial input to this convolutional layer will be same. We are going to change only the depth. In that case, the output depth will be 32 because the filters are 32. Then in order to reduce that spatial dimension, the width and the height, we are going to use the max pooling 2D layer. So this is going to reduce the width and height by half. So for example, if the input is 32 by 32, the output from the max pooling 2D will be 16 by 16 because we have defined the stride to 2 2. Then we are going to pass that information to another convolutional layer. Again, the stride is 1, and then again to this max pooling 2D layer. So if it's 16 by 16, then we will get 8 by 8 from max pooling 2D, and the depth will be 64 because above this max pooling 2D we have passed our data to a convolutional layer with 64 filters. That's why the depth will be 64. And finally we are flattening it and passing it to a dense layer, and the number of units of this dense layer will be equals to the latent space variable, which in our case again is going to be 2. So this is how the encoder code will look like. Obviously we are going to follow the object oriented approach, and there will be some more extra lines of code, but the core of the encoder looks like this. Now let's talk about the decoder. So the decoder is very simple. First of all, we are going to now convert our latent space back into the image. So that's why the first layer is going to be dense layer with 7 into 7 into 64 units. So you can like take out the calculator and calculate how many units is going to be there, and then we are going to reshape it to 7 by 7 by 64. That's pretty good. And then we are going to pass the input to convolutional layer with 64 filters 3 kernel size and stride variable 1. So the special dimension will remain same, 7 by 7. Then we have the upsampling 2D. It's like the opposite of max pooling 2D. Max pooling reduces the special dimension and upsampling 2D increases the special dimension. So it will increase the width and height from 7 by 7 to 14 by 14, and then we are going to pass that 14 by 14 by 64 to another convolutional layer with 32 filters and 3 kernel size. Again, stride 1, ReLU activation, padding is same. So the output from this convolutional layer will be 14 by 14 by 32, and finally we are passing it to another upsampling 2D, so the output will be 28 by 28 by 32. And finally, when I pass my 28 by 28 by 32 from this last convolutional layer, the output will be 28 by 28 by 1. This means now the input to our encoder was 28 by 28 by 1, and the output from this decoder is 28 by 28 by 1. So both are same. This means it's an unsupervised technique. We can use the input data as a label in order to train this model. Now here is an important note, and that is we have not used transpose convolutional layer, although TensorFlow provides us transpose convolutional layer and it's a learnable layer. This means we have weights, but still we are not using it. The reason is that it produces checkerboard like artifacts. So I'll provide the link to the file in the description where you can learn more about these checkerboard artifacts. So that's why I'm going to stick with the convolutional layer and the upsampling layer. Okay, obviously you can try on your own that transpose convolutional layer, and in the next video we are going to implement the actual code and we'll train the model, and I'll see you there. Bye bye.